right there, AP Chem scholars. Let's finish out Unit 2 with a little Vsepr and hybridization. And yeah, I know it looks more like Vsepr. I don't know why people pronounce it Vsepr. I guess it just rolls better. So, Vsepr really stands for valence shell electron pair repulsions. When we draw our Lewis structures, we're always talking about them in electron pair, right? We know that orbitals hold 2 electrons, and so these electron pairs will repel one another and spread out around the valence shell as much as possible. So that's really the basic idea here. Opposites attract, yes, but likes repel. So we're going to try to minimize those repulsions in 3-dimensional space as much as possible. So we have to start with a discussion of domains. So domains are regions about an atom shell where valence electrons are concentrated. In a Lewis structure, we just look for bonds and non-bonding pairs. Now keep in mind that a double bond or a triple bond is one domain because these electrons are in one region. That's what makes the double bond or the triple bond that much stronger, is that there's a concentration of charge in that area holding the atoms together. Let's look at a couple other examples real quick. All right, so carbon in this case has 2 domains, 1, 2. The phosphorus has 5 domains. The nitrogen has 4 domains, 1, 2, 3 bonding, 1 non-bonding. Whereas the sulfur here has 1, 2, 3 domains. All right, so we need to be able to count off those domains so that we can talk about how they're spreading out those electrons. So in this case, the carbon should have 4 domains. The nitrogen, well, we just saw something like this, has 4 domains. And this oxygen has 1, 2, 3 domains. Yay. All right, so first thing we have to talk about is the idea of domain geometry. Domain geometry is the basic idea of spreading out the domains as far as possible to minimize those attractions. Again, that's really the whole basis of the Vsepr system, is this domain geometry. So if I had 2 domains, like in the example that I had up there with HCN, to keep those domains as far apart, they'd have to be 180 degrees. If I go to 3 domains, now I'm putting them out to 120 degrees. When you go to 4 domains, you might think that it would be 90 degrees, but once we get out to 4 domains, now we start going 3-dimensional. 3-dimensional geometry is a bit of a pain in the butt. So when we talk about this domain geometry, it's really just related to the number of domains. When there's 2 domains, we call it linear because it is 180 degrees apart. When there's 3 domains, we call it trigonal, 3 angles, planar. Okay? There are 3 equal angles of 120 degrees in that flat molecule. When you go to 4, now we get something that is tetrahedral. Hedral means sides. They think of this as a 4-sided thing. You see them drawing in that little pyramid in there to try and represent it. Whatever. The angle works out to be a nice 109.5 degrees. When you get to 5 domains, it's literally the 2 domains and the 3 domains smushed together. So the 180 is right here from top to bottom. So if I could isolate just on these 3 atoms, you'd see the same thing as these 3 atoms. But we also end up with these 90-degree angles because in the middle of that, we have an entire other plane. So they're 90 degrees apart from either of the top or bottom. And inside that middle plane, we have the trigonal planar part. Those 3 there would be like those 3 there. And so we have 120-degree angles. So it's really 90, 120, and 180 in this mashup. And when it's 6 domains, we call it octahedral because oct, of course, means 6. No, 8-sided. So it's a double pyramid, so you'd have to really see the idea. But again, I guess it's like looking at the stars and seeing dragons and whatnot. So octahedrals, all of them are 90 degrees, but technically there's always 180s because there's always an opposite to whichever one we're talking about. So 90s and 180s. However, when we talk about the actual shape of a molecule, it's really not going to match up to domain geometry. So this picture here shows water. And now in the water, first of all, you notice that they're not straight across, and the angle is 104.5, let's say, which isn't on that chart at all. Well, there's really a couple reasons to the why. First off, when we talk about the shape of molecules, we're only looking at the atoms, so non-bonding pairs fall out of the picture. This oxygen really should have two non-bonding pairs. And the other side of it is non-bonding pairs tend to squeeze bonding pairs down. So instead of the angle, because the oxygen has 4 domains, instead of the angle being 109.5, those two non-bonding pairs squeeze the angle down to 104.5-ish. So we're going to see a couple things like that along the way. Just keep in mind, as far as non-bonding pairs, when the central atom has non-bonding pairs, with exceptions, and I'll talk about those exceptions, we expect the angles to be a little bit smaller than they would be otherwise. So again, here's a water molecule, and that representation of the 104.5, like we talked about. All right, so we're only looking at the atoms. Whenever the AP asks you for the geometry or the shape, they're talking molecular geometry, not domain. So you do not need to include domain geometry unless asked specifically for domain geometry. So if it just says geometry, if it just says shape, they're talking molecular geometry. So let's get into molecular geometry. Before, when we said there were two domains, we expect it to be linear. Well, if we have two domains, they have to be bonding domains. There are 0 non-bonding domains, and so we call the molecular geometry linear. Whenever there are 0 non-bonding domains, the molecular geometry and the domain geometry will be the same. That shouldn't say domain, it should say molecular. Oh no, I know what I was going for there. Okay. We're talking about two domains overall and the molecular geometry. All right, I'm not totally losing it. Sorry. Let's continue. Now, when you go to 3 domains, we talked about the domain geometry being called trigonal planar. So again, what if there's 0 non-bonding? Well, when there's 0 non-bonding, the domain and molecular are the same thing, so it's trigonal planar, such as boron trifluoride here. But with 3 domains, there is another option. I could have 2 bonding and 1 non-bonding domain. So, for example, here we see a bonding domain, and a non-bonding domain. So now when we look at this, we've got to kind of ignore the non-bonding pairs when we talk about the shape of it, and it has this inverted V or caret symbol. Okay, so we call that a bent molecule. Now the angle, because it's 3 domains, should be about 120, but again, since there's a non-bonding pair, it's really going to be somewhat, a little bit less than 120, if we're getting technical. For now, just say about 120, that's fine, but understand that non-bonding pair again would throw it off. So let's go to 4 domains. There's going to be 3 different options here. If there are 0 non-bonding, domain and molecular are the same thing, it's tetrahedral, like in this methane molecule. The carbon has 4 bonds, no non-bonding. That is a tetrahedral geometry. When we go to 1 non-bonding pair, we take something like ammonia here. We see that we have 3 bonding domains, 1 non-bonding. So now they decided to call this one a trigonal pyramidal. So it's almost the same as the tetrahedral, except that instead of having another atom up here like we did with the methane, we have that non-bonding pair. And notice how they exaggerate the size of the orbital that this non-bonding pair is in to emphasize that it's going to squeeze the angles a little bit. So instead of angles of 109.5, it's going to be a little bit less. What if we have 2 non-bonding domains? All right, so that's the water molecule we were talking about before. We have 2 bonding, 2 non-bonding domains. So again, we have that V or inverted V, whichever way you want to talk about it. We also call this bent. So there's 2 different bents, but the angles are very different. So you have to be careful about that when it comes to our bond angles. If it's based off of 4 domains, the angle is based off of 109.5, and again being shrunk down a little bit. If it had 3 domains, then it's based off of 120 and probably shrunk down a bit as well. So let's go do 5 domains. Now we're going to have 4 domains. When there are 0 non-bonding domains, the molecular geometry is the same as the domain geometry, so it is called trigonal bipyramidal, like this phosphorus pentafluoride. So we have our angles of 90, 180, and 120. Don't worry about bond lengths. That's not something we're going to get into. When there is 1 non-bonding domain, it comes out of that central area. So again, this being the central area where there were 3 atoms in the one plane, well, 4 technically in the plane. We take off one of those, boom, and we end up with our seesaw molecule. So sulfur tetrafluoride is a seesaw. Now we have a non-bonding pair, so notice that instead of angles of 120 or even 180, the angles are shrunk down a bit. That's okay, don't worry about that. It's just going to happen. When there are 2 non-bonding domains, we take off another one out of the middle. So we pop off this, and now we're left with this T-shape molecule. And again, technically the non-bonding pairs shrink the angle, so instead of being 90 and 180, no 120s anymore, by the way, 90 and 180, we're really going to get a little bit less than 90 and a little bit less than 180. And there is another option where we go 3 non-bonding domains, and now we get something that is linear again. So we got rid of all 3 out of the central, and we're left with this. Now this is a rare case where there are electron pairs on the central atom, lone pairs, and it's still going to be symmetrical. These 3 are going to balance each other out so that it does not affect the angles. The angle will definitely be 180 on this. No 90s, no 120s, only 180 degrees in this case, because we only have those 3 atoms in a line. All right, so let's go out to 6 domains. We're going to talk about 3 options here. When there are 0 non-bonding domains, the molecular geometry is the same as the domain geometry. It is octahedral, like sulfur hexafluoride. Okay. Then when we get in 1 non-bonding pair, we pull off one end of it, and we get something that looks like this. Well, they call that a square pyramid, or square pyramidal geometry. Again, the angles should be 90s and 180s, but the 90s might be shrunk down again because we have a non-bonding pair. I just keep re-emphasizing that. Hopefully you will remember for follow-up questions. And lastly, when there are 2 non-bonding domains, we say the molecular geometry is square planar. All right, so that's xenon tetrafluoride here. We have 2 non-bonding pairs, and again, this is the other rare case where we have non-bonding pairs, but it is still going to be symmetrical. These lone pairs are opposite each other, so they kind of cancel each other out, and so they don't squeeze any of the angles at all. So here's a chart summarizing that whole thing. Notice I put the about 120, about 109, etc., all those things that we kept talking about when there are lone pairs. However, I should actually get rid of that there. That is exactly 90. Okay, better. So what is domain geometry and the molecular geometry of these? Pause the video, give them a try. I'm going to go on. So carbon dioxide, we already saw represented on one of the other slides. That's linear geometry and linear domain and molecular geometry. Methane, again, was represented on one of the slides. It has a total of 4 domains, and they're all bonding, tetrahedral, tetrahedral. Xenon tetrafluoride was one of the last ones we saw. It has 6 domains, and 4 of them are bonding. So even though the domain geometry is octahedral, the molecular geometry is square planar. H2CO, I don't believe we saw represented in there. The carbon has a double bond to the oxygen and single bonds to the hydrogen, so it has 3 domains. There are no extra electrons, so trigonal planar, trigonal planar. Water we saw several times. The oxygen has 2 non-bonding pairs and 2 bonds, so that means 4 domains, tetrahedral. But since only 2 of them are bonding domains, it is a bent geometry. xenon difluoride. The xenon is making bonds with 2 of the fluorines, but it would also have 3 non-bonding pairs. So even though it has a total of 5 domains and is trigonal bipyramidal, it would have a linear molecular geometry. Phosphorus pentachloride was represented on one of the molecules. Okay, it has 5 domains because each of the chlorines has a bond to phosphorus, trigonal bipyramidal. There are no extra electrons on that phosphorus, so it's also trigonal bipyramidal molecular geometry. And iodine pentachloride. The iodine makes bonds with each of the chlorines, so that's 5 domains, but it has a lone pair, so it would have 6 domains total, so it's octahedral for the domain geometry. But since one of them is non-bonding, we would call it square pyramidal. All right, so the electron dot structure of carbon shows 4 unpaired electrons, but the orbital notation only shows 2. Why? Will carbon make 2 bonds or 4? Well, the reason that this is shown one way and this is shown another is that this represents what we call a hybridized carbon atom, where this is unhybridized. When we usually start off with just the Lewis symbols or electron dot structures, we usually do it unhybridized. So it really should have shown a pair and 2 lone ones. But most atoms tend to hybridize, and let's talk about what that is and why. So hybridization, a hybrid means that you're mixing things, okay, and taking properties of both, making some amalgam of them. When we talk about bonding, we like the idea of s orbitals being involved in bonds because you don't have to line them up. Remember that the s orbitals were kind of spherical, so it's very easy for an s orbital to bond to something else. However, s orbitals tend to pair up right away. So if I want to get this s orbital involved, I have to kick out one of the electrons and bump it into one of the p orbitals. That's the process of hybridization. And we're going to shift electrons around and shift energy to make a new set of orbitals that are now all equal in energy. You may remember from when we talked about the Aufbau principle, the fact that s and p's had different amounts of energy. In the hybrid, we're going to mix one s orbital with 3 p orbitals, and we're going to now take the fact that even though these p's had more energy than the s, we're going to shift energy around so that all 4 of these things now have equal amounts of energy, and we're going to form a hybrid that we're going to call sp3. Look at the number there. S, there's no number written after it. We'd assume that's a 1, right? In chemistry, if there's no number, we assume 1. P has 3. So that's a total of 4 orbitals that are involved in this. The number of orbitals does relate to how many bonds. Okay. Here's the Aufbau principle idea again about the difference between S and P. They should have different amounts of energy, but when we hybridize them, now all of them mix together and we have just one set of orbitals that we're calling sp3. So it's just the idea that they're all equal. They're going to look the same, where an S and P's had different shapes. Now the sp3 looks like this. You see a little bit of the P character, but a little bit of the S, almost like a little ball over here. So we get these hybrids for sp3. Now again, there are 4 of them in there, right? So that makes sense that it would be able to handle 4 domains. So 4 domains forms a hybrid of sp3. When it's 2 domains, we only need 2 orbitals. So we take an S and a P, and that gives us 2 domains. When I want 3 domains, I need 3 orbitals. So I take an S and 2 P's. Now the problem comes when I get to 5 domains, because there's only 3 P orbitals in any subshell. So if I take an S and 3 P, now I have to go to a D and bring that in. And that's why elements after silicon are the only ones that could exceed an octet, because they have to be able to be in the 3rd energy level and have enough electrons to spread out. Silicon, even though it is in the 3rd energy level, only has 4 electrons, so there's no way it could spread out to 5 orbitals. But phosphorus, the next element, does have 5 valence electrons. It could spread out into 5 orbitals. Likewise, sulfur, the next element, has 6 electrons, so it could spread them out into 6 orbitals, okay, to form 6 domains. And so that would mean we need 6 orbitals, so 1s and 3p is 4. So we take 2d, that gets us to 6. So the hybrids is just based off of the domains. So we've talked about these molecules already. You should be able to talk about the hybridization of them very easily. Pause it, give it a try. I'm going to go on. Carbon dioxide would be sp. The methane would be sp3. The xenon tetrafluoride would be sp3d2. The H2CO would be sp2. Water is sp3. Xenon difluoride is sp3d. Phosphorus pentachloride is sp3d. And iodine pentachloride is sp3d2. Now we're going to talk briefly about the idea of sigma and pi bonds. I don't know that this is a big thing with the AP anymore, but I like to cover my bases just to be safe. We mentioned that s orbitals are usually involved in bonding. Okay? So initially, when they talked about a bond between s orbitals, they called it sigma because sigma is the Greek letter for s. However, they realized over time that a sigma bond is really not always involved just with s. It is most of the time, because we just talked about the idea of these hybrids, and every hybrid that we looked at in the chart had some kind of s involved in them. They felt, all right, that's still okay to talk about a sigma bond. But a sigma bond is really just that primary bond that occurs along the axis that would connect the two nuclei. So along this line, the protons in this atom are attracting electrons in this atom. The protons in this atom are attracting electrons in this one. And that's what the sigma bond is, right there. That is our primary bond. Every bonding site always has a sigma bond. But it actually can occur once in a while between two p orbitals. For example, between chlorine and chlorine or fluorine and fluorine. Those diatomics actually don't hybridize. Don't sweat that, but it's just something that does happen. But you'll see that everything else either involves an S or an S hybrid type of thing. So we're still going to say that sigma bonds are the primary bonds that happen everywhere. But you can only have one sigma bond in any location. So this would be a sigma bond. 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 One of these would be a sigma bond. And now we have to talk about the fact that when we have double or triple bonds, what's going on there. So the carbon here we see has three hybrids, three domains. And so its hybridization would be sp2. So that means there's an extra p orbital hanging out there. That's where we're going to get this pi bond. Pi is a Greek letter for p, and so they call it a pi bond. What happens is after the sigma bond forms between these two carbons, these p orbitals decide they're going to share electrons, and they slowly start merging, and we get this weird, I don't even know how to call it, the gum-like shape, I don't know. But the p orbitals just merge on both sides, and that's why pi bonds are so much stronger, because we get that extra rigidity because it's surrounding the sigma bond and adding more strength to it all the way around it. So a pi bond is what's going on with an unhybridized p orbital. It's the extra bond. So going back to our image here, one of these is a sigma bond, the other one has to be a pi bond. You can only have pi bonds when you have double bonds and triple bonds. A double bond is always one sigma, one pi. And if we were to talk about a triple bond, it's going to be one sigma and two pi bonds. And again, same idea here. The hybrid for this, the carbons, there's one domain here, one domain here. So that's two domains. That's an sp hybrid. So technically, this carbon has two p orbitals that are not being hybridized. And so it can make extra bonds out of both of those p orbitals. So you see, again, that weird stretched out shape. We have a pi bond above and below. That's one of them. And then in front and behind, we have another one. That's the other pi bond. So a triple bond is always going to be one sigma bond, which is the line between the carbon-carbons here, and then two pi, one here, one here. So very simply, once in a while, you're asked just to evaluate sigma and pi bonds. Okay, so looking at this, again, every bonding site has to have a sigma bond. That's a sigma, 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 that's a sigma. One of these is a sigma, the other one is a pi bond. So there's only one pi bond in this whole thing. All the others are sigma bonds. So it technically works out to be 11 sigma bonds and one pi bond. All right, I know this is a long one. Sorry, but I'm going to just keep pushing on. Feel free to pause, go walk away, whatever. But we need to talk about polarity as well. Bond polarity, we had said, was due to the electronegativity, the difference. The fact that oxygen is stronger than hydrogen means it's not going to share electrons equally. So the hydrogen from this, the electrons from this hydrogen are being pulled towards the oxygen, and the same thing here. So we're pulling down and to the left, down and to the right. Well, vector-wise, to the left and to the right part are going to cancel out, but they were both pulling down. And so you'll see we put this little negative here to say that this end is the negative end of the water molecule. And so by contrast, that has to be the positive end of the water molecule. When we talk about polarity, sometimes we use the term dipole moment. A dipole moment is a vector representation of that pull on electrons. And so let me draw that on the board here and kind of explain that idea briefly. So chlorine is a little bit more electronegative than nitrogen. So the pull of electrons is this way. So we would actually represent it by a dipole moment. It's an arrow, but there's kind of like the plus at this end to say this end's more positive, the pull is that way. So there'd be a dipole moment this way, there'd be a dipole moment this way. Okay, so we're going, now technically, remember that this should be a trigonal pyramidal. So let's actually represent it that way real quick. I'm going to kind of draw it three-dimensionally, put a little shape there to it. So this is down and to the left, this is down to right, this is down and in the back. So what we would have is a dipole moment pulling, I got the wrong black one again. Down and to the left, down and to the right, down into the back. So you see they're all basically pulling downward. So the dipole moment, we would say, is probably negative here and positive here. The outer elements are supposed to be the ones that are more electronegative. So the negative sign should generally be towards the one of the outer ones or in between outer ones or something like that. But these are dipole moments. Now, if we were talking about it for sulfur trioxide, okay, we have three domains. So really, we know that this is supposed to be trigonal planar. So let's try and draw it a little bit more trigonal planar-ish for the moment. Okay, oxygen is more electronegative than sulfur, so we have this one pulling straight up, this one pulling down a little bit and to the right. This is pulling down a little bit and to the left. The left and the right are going to cancel out. And the fact that this is a little down and this is a little down is going to counteract the fact that this is up. This is going to be symmetrical, so it is nonpolar. And really that's all it comes down to is the idea of symmetry. So you have to kind of envision these geometries, because sometimes when we draw it like this way, we make it look like these are 90-degree angles, but they're not. Okay? So a Lewis structure can be misleading. Sometimes we like to draw it by the geometry in a way that's sometimes referred to as a ball and stick model. In any event, when we talk about polarity, we're going to talk about symmetry. And so we have to see, is it perfectly symmetrical or not? Okay. You might look at this and say, well, this is symmetrical. If I split it down the middle here, it is symmetrical. True, but if you look at it from a different line of action, okay, there's two hydrogens below the oxygen, but there's no hydrogens above it. That is not perfectly symmetrical. Whereas this one, if I split down the middle this way or this way, it's going to be symmetrical. So this is a symmetrical model, which means this one is nonpolar, but this one is asymmetrical. It is polar. Okay, so again, this one, and again, misleading because it's tetrahedral, But this one, all of them are going to be, they're not all going to be balanced, I'm sorry, because the chlorine is different than the hydrogens. So there's definitely going to be more of a pull towards the chlorine end of things. So this is going to be polar. And notice the little Greek delta. It almost looks like an 8. It's actually like a cursive D, if you will. The delta positive, delta negative. On my drawings, I was just writing plus or minus. Sometimes you see the delta plus and delta minus, just trying to indicate where things are going with this. Now, this is carbon tetrachloride. Now we see that the carbon is being pulled by chlorines. And again, even though it may not look it from the picture, that's got to be symmetrical because the tetrahedral, there's no non-bonding electrons, so it's got to balance it out to as much as possible, so it will be nonpolar. So going back to the table, let me scroll up here and go all the way back to here. There are 5 geometries that are always going to be polar, and 6 if you count bent twice. A bent geometry is always polar. Trigonal pyramidal is always polar. There's the bent again. Seesaws are always polar. T-shaped are always polar. And square pyramidal are always polar. So those 5 shapes have to be polar because of the non-bonding pairs. Now again, there are 2 times where there's non-bonding pairs. Square pyramidal, square planar, and linear from 5 domains. They can have non-bonding pairs and still be nonpolar. All of the other shapes are nonpolar if the outer elements are the same. What do I mean by that? Let me go back to my view of here real quick and talk about an example like HCN. Now, when we talk about symmetry, these are not the same elements. Nitrogen is more electronegative than hydrogen. So even though, I should use the same color, there's a pull here, technically, there's also a little bit of pull here. Hydrogen is one of the rare cases where the outer element does not have to be more electronegative. There's a net pull this way, so this is polar. Okay, so it is linear, but because the outer elements are not the same, it is polar. Again, notice the fact that the phosphorus has no non-bonding pairs. It's surrounded by the same element. Whether you drew it to look symmetrical or not, this is a symmetrical molecule. This would be nonpolar. But if one of the chlorines, or even 2 or 3 of them, even 4 of them, became fluorines, now it would become polar because it loses its symmetry. Wow, this is a long video. I apologize, but you know, sometimes you just got to get through these things. Where am I? Symmetry. Yep. Oh, that is the end. Well, what do you know? There you have it. That's all of Unit 2. Now we just need to do the practice. All right. Ciao for now.